Our presentation is going to be on organic acid use in leather processing. George is going to give you the history of leather tanning. I, myself, Avery, are going to talk about collagen and the effects of acid agents. Varun is going to cover reaction mechanisms that occur in the leather processing. And to wrap it up, Afeef will talk about environmental impacts.
To understand why the leather making process is as complicated as it is, we need to understand collagen. Collagen makes up 29% of the proteins found in mammals, and it helps give skin its strength, elasticity, and waterproofness. In the leather making process, all three of these qualities need to be disabled so that dye can infiltrate the skin and turn its color. So the molecule of collagen consists of amino acids like glycine and arginine. These are held together by peptide linkages, and like DNA, they can hydrogen bond to each other.
Initially, skins and hides were preserved using a smoking process. However, the smoking process did not serve to fully impede the active decay and only needed to halt it for a limited amount of time. As time went on, they discovered that the use of organic acids with a follow-up base solution were able to preserve the hides for an extended period of time that either limited or fully eradicated all forms of decay. The first process was developed thousands of years ago and involved the use of tannins as the organic acid in question. Tannins were produced by grinding up the bark of oak, beech, or willow trees, and then putting into a solution with soft or mostly chemical-free water. This was then used over the course of many months to allow the collagen fibers within the leather to expand and then dehydrate through the tannin bonding with the collagen molecules itself. The hides and skins would be removed from the tannic acid and then placed into a lye solution to remove the remaining tannic acid from the collagen molecules and produce a final product. This process is commonly called vegetable tanning and was a more green and original process. However, due to the tannic acid's relatively weak acidity and also propensity to react with any hard molecules such as metals that were present in the water, and then also any blood that was still present in the skin, causing discoloration within the final leather product. It was replaced in the mid-1800s with chrome tanning, which was a faster process and used formic acid as the base acid to allow the preservation agent to penetrate the collagen molecules.
Most alteration to this collagen is carried out in two processes called liming and pickling. In the liming process, hides that had just been unhaired are soaked in an alkali solution that generally consists of lime and sodium sulfate. This causes the collagen molecules to swell. The forces of this swelling lead to a general loosening of the fiber network layer, further causing a splitting of larger collagen fibers. The total effect is that liming produces a pelt which swells more at all pH values than does native unlimed skin. So essentially, this process wipes clean the surface of the skin so tanning agents can begin to penetrate. These now limed skins need to be adjusted to a suitable acidity for tannage by pickling. The skins are agitated in a solution of salt and sulfuric acid, for example, until they are at or near an equilibrium of a pH value from 1 to 3. The reason for this acid addition is to slow down the growth of microorganisms along with protonating the basic sites of collagen, allowing for the tanning agent to go deeper than just beyond the external layer of skin. The reason for the salt is, while previously we had caused the collagen fibers to swell, too much of this can damage the skin, and adding salt alleviates this issue by removing water.
Alright, so I'm going to explain the mechanism behind the tanning process. First, we want to make the collagen on the skin much more porous than it is, so that we can dye the skin to form leather. To break up the collagen chains, raw skin is submerged in a basic environment. Here we have a pretty basic addition to the carbonyl, leading to the cleavage of a terminal amine. So, to understand the reaction, we go to the carbonyl's second most important resonance structure. We get rid of this bond here, call that O minus, and the carbocation here. So it's pretty easy to see where the hydroxy group will add, right here at the carbocation, which it does. So then we get an OH here. And then the proton hops from the oxygen to the nitrogen. And we get that, and positive charge follows onto the nitrogen. Then this is where the carbon-nitrogen bond cleaves, right here. And so this breaks up, the charge goes away, and we're left with a terminal amine on the right and a carbocation on the left. And then we can see how the carbonyl is regenerated here, leading to the double bond there. So this shows how collagen is made more porous. This happens throughout. There's multiple carbonyls in one chain. So in a basic environment, this happens throughout the chain. So this shows how the collagen is made more porous. But how do we actually prepare the skin to be dyed? To explain that, let's take a trip to Forney's latest smart TV. So to understand how the dye actually inserts itself inside the porous collagen, we need to look at the arginine side chain that forms a carboxylate. So this reaction occurs in an aqueous base, and the double bonded nitrogen pulls off a proton from the water, leading to a carbocation here. And this is where the hydroxy group adds. Then a proton hop occurs here, creating NH3+, and that makes it a good leaving group. And what do good leaving groups do?
They leave.
And so that's exactly what happens. The NH3 leaves, creating a new carbocation where the second base adds. Another proton hop occurs, creating NH3. NH3 is a great leaving group. And what do good leaving groups do?
They leave.
And that's exactly what happens here. The NH3 leaves, and the carbonyl is regenerated from this O minus, leading to the carboxylate up there.
Next, we will address some environmental concerns with the leather tanning process. Since the process is primarily done in a water medium, there is a high risk for environmental issues to arise. The main waste products of the process are sulfides, chromium salts, dye stuffs, hair, wool, alkali, and various acids. The majority of these byproducts are actually pretty easy to deal with. The acids and alkalis can be used to neutralize each other, while any excess can be cheaply neutralized as well. Hair and wool can be sent off to other industries that use them, and salt content would be relatively easy to deal with this day and age. The chromium salts and sulfides, however, are a lot more difficult to deal with. First, let's talk about sulfides. The biggest concern with sulfides is that in the presence of neutral or acidic solutions, sulfides react and produce hydrogen sulfide, the same compound that infamously gives a rotten egg its terrible odor. Aside from just smelling bad, hydrogen sulfide is also toxic and corrosive. So it wouldn't just be a health concern for sewage workers, it could also erode the sewer walls. Now let's briefly discuss the harmful effects of chromium salts. Chromium salts result in two different issues. First off, chromium salts poison many of the microorganisms used for sewage treatment plants, therefore resulting in the process being done improperly. In addition to this, the chromium salts react to produce chromium hydroxide in the presence of neutral or near neutral solutions. This would result in the buildup of chromium hydroxide in sewer sludge that would later be used as fertilizer. That concludes our presentation. Thank you so much for watching, and I hope the information that we provided will be of pertinent use. If you have any questions regarding the process, please feel free to leave us a comment and we might get back to you.